In this video we are going to explain how to program a positioning system based on a square wave relative encoder with a PLC. How the Quadrature encoder works? The code disk inside a Quadrature encoder contains two tracks usually denoted channel A and channel B. These tracks or channels are coded 90 electrical degrees out of phase. And this is the key design element that will provide the Quadrature encoder its functionality. To know where direction sensing is required, a controller can determine direction of movement based on the phase relationship between channels A and B. As illustrated in the example optical encoder figure below, when the encoder is rotating in a clockwise direction, its signal will show channel A leading channel B. And the reverse will happen when the Quadrature encoder rotates counterclockwise. In our example we will use one of the machines available in Machines Simulator, the packaging merchandise distribution. If you do not have this machine installed, you can download it from the Nerdec forum. Link in the description. In this machine the objective is to classify 3 different types of bottles in a packaging line. The blue bottles should be sent through the first output line, using loader arm 1. The gray bottles must be sent through the second output line using loader 2. And the transparent bottles must continue through the main bottling line. The camera located in the conveyor start must be used to detect the type of bottle, and the encoder located on the conveyor motor to control the position of each bottle that must be sent to each output line. We also have a photo cell that will help us to control some security conditions that will be explained during the resolution of the PLC program. The encoder is installed together with the shaft of the conveyor motor. To carry out the PLC programming, we will use EasyPLC, the PLC emulation software included in the EasyPLC software suite package, but any other automation software can be used. First, let's see the machine in operation locating each of the key elements. Using this system, we can see how with only the encoder and using appropriate programming, the position of each element that enters the conveyor can be known to the millimeter based on the resolution of the encoder. In this way we avoid the use of sensors or photocells positioned in each place where they must be detected to carry out any action, in addition to avoiding adjustment or maintenance operations of these sensors. Every time a bottle is detected in the reading station, the PLC saves the value of the encoder in a stack that will increase each time the same type of part is detected. The stack will have the length of the number of bottles between the reading station and the exit station. In total, 2 piles are handled, one for the blue bottles and the other for the gray ones. The pile of the blue bottles has a length of 3 and that of the gray ones of 5. The PLC will verify the value of the upper element of each one of the stacks. If this coincides with the value of the encoder, plus a specific offset belonging to the distance between the reading station and the output station, it means that there is a bottle in the right area to be evacuated, so the PLC will execute the bottle unloading routine, activating the corresponding robotic arm management signals. At that same moment the stack is adjusted, raising each value and resetting the last one. The offset that indicates the distance between positions is initially calculated empirically, seeing how many encoder steps there are between the reading and output stations. Now let's see how the PLC program is set up. The PLC program is composed of 4 sequences plus one initialization, 2 functions, and 2 data stacks. In the encoder reading sequence, the 2 digital signals of phases A and B of the encoder are read. In this example we see how the signals for the encoder count are programmed, both in the forward and reverse directions, although in this program it will only work with the forward direction. If we pay attention to the encoder diagram, to program the signal cycle for the forward direction, we first see how channel B is off and channel A goes from off to on. We see this in the condition of the first segment. Next, we have channel B on, and we see how channel A goes from on to off. The next state is channel on and channel B goes from off to on. Finally, channel A is off and channel B goes from on to off, after which this process is repeated cyclically. In this way we are able to monitor the encoder signals so that they count up. To manage the countdown, in the case we must do so, we can see the signal control scheme in the following program segments. Main sequence, here the management of the buttons, start, stop and emergency button is programmed, setting the conditions to start or stop the program. In the following segments we have the management of the conveyor, and finally the management of the camera. In this case, when we have a bottle at the input station, camera, we read the value of the detected part type, and the function is called to fill the stack. It is important to see the safety condition thanks to the photo cell, which activates the enable reading Boolean variable, which will allow us that if the emergency or stop button is pressed, the stack does not reintroduce the same value of the bottle that it already present in the reading station when the machine is started up again. The following sequence, ARM1, controls whether a bottle of the blue type is present in the output zone to be removed by ARM1. To do this, the first position of the stack for the type of blue piece is controlled. If the value of the encoder is the one that had the blue bottle in the input station plus the offset that indicates that the bottle has already reached its destination, then the following actions are done. We use the register transfer command to run a position in the stack, and thus we update the values so that the stack works in FIFO mode. We reset the last value of the stack. We subtract 1 unit from the index that calculates the pointer to where the stack points to be filled again. And we activate the sequence so that the arm begins to move and unloads the blue bottle on the starting line. Below is showed the graphic or sequence of 6 steps to move the robotic arm and deposit the bottle on the output line. The last sequence handles arm 2. It is exactly the same, but with the signals to handle the second stack and move the second arm. Now we have the two functions, FIFO1 and FIFO2, that are responsible for filling the two data stacks with the values indicated in the ARM1 and ARM2 sequences. Here the stack is filled with the value of the encoder plus the offset that is equivalent to when the bottle will arrive at its destination, and the pointer index will be incremented to push the next value into the next stack position. Finally, we see the two data blocks that contain the data arrays that will be used as FIFO stacks by the program. They are integer data blocks. In the initialization sequence that is executed as soon as the PLC starts execution, the value of the init stack variable is loaded, initialized to the value -1 in the two data blocks. With this we avoid having the value 0 in the stacks that could give errors when the encoder also has the value 0.